Just when humanity believed it had a solid grasp on the origins of the cosmos, the James Webb Space Telescope hurled a cosmic curveball into our understanding, forcing scientists to rethink everything we thought we knew about the birth of the universe. The latest discovery from this technological marvel challenges the very foundation of the Big Bang Theory. For decades, we have been told that the universe began from a singular, dense point of unimaginable energy that expanded rapidly, giving birth to the galaxies, stars, planets, and life we know today. Evidence such as Hubble's law, which shows distant galaxies speeding away from us, the cosmic microwave background radiation, the abundance of primordial elements, and the large-scale structure of the universe all seem to reinforce this idea. But now, JWST's extraordinary ability to peer deeper into time than ever before is revealing that the story is far more complex, and perhaps far stranger than we imagined. The question of what happened before the Big Bang has long haunted cosmologists. While the Big Bang Theory elegantly explains how the universe expanded and evolved, it has never been able to answer what triggered it or what came before it. That missing piece might be the most important clue to understanding existence itself. Some of the most compelling theories aim to explain that elusive moment before the beginning. One is the Big Bounce hypothesis, which envisions the universe not as a singular event but as part of an infinite cycle of expansion and contraction. In this model, a previous universe collapsed under its own gravity into a singularity, only to rebound and expand into the cosmos we inhabit today. This cyclical process may be driven by quantum forces, gravitational effects, or even hidden dimensions beyond our perception. Another is the ekpyrotic scenario, which imagines our universe emerging from the collision of two vast brains floating in a higher dimensional space. The collision unleashed a burst of energy, causing a period of rapid inflation that smoothed out irregularities and created the seeds of galaxies. This concept even allows for the possibility that brain collisions happen repeatedly, giving birth to countless universes. The pre-Big Bang scenario takes yet another approach, suggesting our universe evolved from a prior state of low energy and high curvature into a high energy, low curvature state. This transition involved a phase of superinflation that magnified quantum fluctuations, which would later grow into the cosmic structures we see today. And then there is the no-boundary proposal, which describes the universe as having no edges in space or time. In this vision, the Big Bang was not a singular point but a smooth, finite state where space and time emerged together from a quantum fluctuation encoded with all possible histories of the cosmos. Each of these theories challenges our imagination, but now JWST's observations are offering tangible evidence that could tilt the scales toward one of them. One of JWST's most groundbreaking findings so far is the discovery of the earliest protogalaxy cluster ever observed, existing just 650 million years after the Big Bang. In the cosmic timeline that is astonishingly early, a period when the universe was still in its formative stages. Initially, matter and energy were spread nearly uniformly across space, but small fluctuations caused by cosmic inflation created subtle ripples in density. Over time, gravity amplified these differences, drawing matter into clumps that would eventually form stars, galaxies, and clusters. In as little as 50 to 100 million years, the first dense regions began to collapse under gravity's pull, igniting the earliest stars. These environments were chaotic, with intense radiation and powerful stellar winds making them turbulent and unpredictable. Small clumps merged into larger structures, producing massive galaxies teeming with heavy elements and rapid star formation. Yet JWST has shown there is still much earlier territory to explore, perhaps even the very first galaxies that ever existed. The formation of galaxy clusters, on the other hand, is governed by surprisingly simple rules. Their development depends largely on three factors: the rate at which the universe is expanding, the initial density variations on the relevant scale, and how quickly gravity can cause matter to clump together. Complex astrophysical processes inside individual galaxies do not significantly affect cluster formation. Gravity is the dominant architect. Before JWST, astronomers hunted galaxy clusters using several techniques. One was to search for groups of galaxies in the same patch of sky that shared similar redshifts, indicating they were at roughly the same distance but had different velocities. Clusters could also be spotted by their X-ray emissions, produced when gas within them became extremely hot due to collisions or starburst activity. These X-ray observations revealed not only their presence but also information about their mass, gas content, and history of mergers. Another method relied on gravitational lensing, where the immense gravity of a galaxy cluster bends and distorts the light from more distant galaxies, creating arcs and magnified images that betray the cluster's location and mass. An example of a mature cluster is CLJ 122, home to 17 galaxies, more than half of which are starburst galaxies producing light 2.7 billion years after the Big Bang. But clusters do not start this way. They begin as protoclusters, loose associations of galaxies that have not yet heated their gas enough to emit X-rays. Using ground-based telescopes like Subaru, KEK, and Gemini, scientists identified two such distant protoclusters, one containing 44 galaxies at a redshift of 5.7, dating to 1.1 billion years after the Big Bang, and another with 12 galaxies at a redshift of 6.6, corresponding to 800 million years after the Big Bang. These structures were in the process of becoming gravitationally bound. JWST's unmatched sensitivity, however, has pushed this timeline back further than ever before. Surveys such as JADES, GLASS, and SEWERS have uncovered even earlier examples. In the GLASS field, aided by the magnifying power of the foreground cluster Able 2744, astronomers detected 7 galaxies at a redshift of 7.8, a time just 650 million years after the Big Bang. This protocluster, named A2744Z7P900D, is now the most distant ever discovered. Its combined mass is about 400 million times that of our Sun, comparable to the present-day Milky Way, and it is expected to have grown into something as massive as today's Coma cluster. Yet perhaps even more astonishing is JWST's detection of a tiny but incredibly active galaxy, RxJ 2129Z95, seen as it was only 510 million years after the Big Bang. At just 105.6 light-years across, it is minuscule compared to the Milky Way's vast 100,000 light-year span. And yet, despite its size, it matches the Milky Way's current rate of star formation, cramming enormous stellar activity into an incredibly compact space. This galaxy's light was amplified and split into 3 images by gravitational lensing from a massive cluster, allowing JWST's NIRSpec instrument to analyze it in detail. The spectrum revealed strong emissions from hydrogen and oxygen gas clouds, indicating intense star formation. Strikingly, there is no sign of an active black hole at its center, which may hold clues to one of cosmology's biggest mysteries, the end of the cosmic dark ages. This was the period when the universe's first light sources reionized the neutral hydrogen that filled space. Whether black holes or massive bursts of star formation were responsible is still debated, but RxJ 2129Z95's lack of a black hole suggests that hot, young stars may have been the main drivers. If more galaxies like it are found, they could account for a significant portion of the ionizing radiation needed to end the dark ages. Measuring their contribution to the ionizing photon budget is now a high priority for astronomers. The James Webb Space Telescope is not just extending our vision further into space. It is reaching deeper into time, revealing a universe that is far richer and more dynamic in its infancy than anyone dared to imagine. Its discoveries are not only filling gaps in our knowledge, but also opening entirely new chapters in the story of the cosmos. The questions it raises about the origins of the universe, the processes that shaped it, and what might have existed before the Big Bang, may redefine cosmology for generations to come. And this is only the beginning. With every new observation, JWST is dismantling old assumptions and replacing them with hard, dazzling evidence from the dawn of time itself. The deeper it looks, the more it shows us that the universe is not a static, predictable history but a living, evolving mystery that began long before we thought it did, and may never truly have had a beginning at all.